starting with the new topic. The new topic is again has the same relation what we did so far. We did superposition of waves. Today we will be doing superposition of waves part 2. Now in this, what you will be learning is how two waves get superimposed with each other. I was discussing about what is superposition of the waves. We already discussed that. Now today we will be doing superposition of waves part 2, and why we say it's a superposition of part 2, because here we will be discussing with respect to the waves which are called as stationary waves, or it is called as standing waves. Now what does this mean? That's standing wave, or it's a stationary wave. What does the word implies over it? Anyone from the class? What does the word implies? Standing wave or stationary waves? Yeah. The question for class. Stationary waves. What does this stationary waves means? On class? No one? Okay. So basically what happens is that we do get standing waves, also called as stationary waves. Standing waves or stationary waves, we say that it appears for us at a one point. It may be vibrating, but for us, the perception will be that the wave is not vibrating. For example, you might have experienced this. If you hold a rubber band from two ends and you vibrate the rubber band exactly at the center, you may get such kind of wave, or it is maybe called as a loop also. So for you, it would be like stationary. So the particles which are vibrating of this particular medium, let's say it's air, they are just vibrating, but you feel that they are at the same point. They are not vibrating, but they are actually vibrating. How do we get this stationary wave or a standing wave? The condition is that, very important condition to get such a stationary wave or a standing wave is that we need a bonded region for this. And without bonded region, getting a stationary wave or a standing wave is impossible. So what is the important condition to get the stationary wave or the standing wave? Anyone from here? What is the important condition to get the standing wave or a stationary wave? Or we use a word bonded region. I'll tell you what is bonded region. To go ahead in the chapter, you need to first understand what is bonded region. And how does this bonded region is classified into two types. Now, bonded region is nothing else but it's a kind of a medium. Why do we need a medium here? Because my standing wave or my stationary wave is nothing else but it's just due to the reflection of the wave. So let's say that this particular wave is originating from here, reaches up to one region and it reflects back. So to get the standing wave or stationary wave, another thing or the condition is that we need the incident wave, we need the reflected wave. And these two rays, when they get superposition, they get their displacement, we get the resultant displacement out of this, then we call such a wave as a stationary or standing wave. So we need two conditions here. One is we need the bonded region. Second, we need the incident as well as the reflected wave from here. This is possible in longitudinal waves. This is also possible in transverse wave. For us, we are just discussing here with respect to the transverse wave. That is possible for longitudinal waves also. Did you get it? What are the two conditions we require for the stationary or the standing wave? So we'll just look at what does the bonded region means and what are the different bonded mediums we have, or we say it's a bonded region. So basically, we have two bonded regions through which my incident wave will reflect or bounce back, and there will be some intersection between the two waves. Okay, superposition. So bonded regions are of two forms. One is the rigid surface, which the ray gets reflected, and the other one is the free surface. My ray can be reflected either from the rigid surface or it can reflect from the free surface. We'll discuss that, what is the meaning of rigid surface and what is the meaning of free surface. Till the time you do not understand what is my rigid surface, what is my free surface, you will not come to know that my reflected wave, where it gets superposition, there it will be a maximum amplitude or it should be a minimum amplitude. All this you will come to know now. When I say rigid surface, I can easily give you one example is that, you play a guitar. Can anyone tell me the two ends of any wire which you vibrate on the guitar? Where are the two ends of that wires connected? Is it a free, or it is connected to, or it is tied at the two ends, or it's left free? So basically we tie them at the two ends. So when I tie at the two ends, I may get the different loops over here. So my rigid surface is when my incident ray reaches up to one end and reflects back. So this surface we call it as rigid surface. Rigid surface is the point where the two ends of a given thread is fixed. We come to the depth knowledge of how does the rigid surface helps us to get the reflected ray, and very important is there any phase difference or is there any change in the phase of my incident ray and my reflected ray? We'll come to that point. When I'm talking with respect to free surface, I'll just give you an example. This is discussed the same example. It's like I have a water inside this, and the wave is incident at this surface. Let's say this is the incident wave. It will reflect back from here and will go in some other medium. So basically what happens is that we have here air and a water over here. So this water will act as the rigid surface. The ray will reflect back and will go in the air. The air over here is my free surface. So the difference noticed here between the free surface and the rigid surface is, this is one example where we say two ends are connected to the rigid point. Free surface is this air in which it's vibrating. This will be called as my rigid surface. If we look into certain examples and we look into the musical instruments, let's have an example of a flute or any such musical instrument which has a membrane. Let's say it's tabla or a drum. They all are classified and they have a bonded region. They all have a bonded region. One may have a bonded region as a free surface. The other example may have a bonded region as a rigid surface. So they get classified here. Let me tell you or give you one example of a free surface. That's the free surface. Okay, for example, if we are talking with respect to a flute, you know that flute has different holes on that. Okay, let's say I close all the 6 or 8 holes of the flute and I blow from one end. There is no way in which the given rays which are incident are reflecting in the air or something, because we have closed all the holes, because of which we get the different note out from them. But if I keep open, the reflected air, the reflected wave which may travel in the air or incident may travel in the air. In this case, we have a free surface over here. So what you need to know is that what happens when such a reflected ray travels in the rigid surface or a free surface. Is there any phase change or there is no phase difference happening when the reflected ray travels from a rigid surface or it travels from the free surface? I'll tell you how we work on this. So once you know what is bonded region, let's just go ahead and see how do we classify them. Okay, so let's say the reflection is taking place. Let's say the reflection of wave is happening in a free surface. Okay, so let me just show you that a wave is traveling in a medium and traveling here like without any bonded surface. There is no bonded surface for such a wave. Let's say that same wave now travels and gets reflected from a free surface. Let's say example of free surface is air over here. Okay. So what happens is that such a wave when it travels, and let's say that at this particular end, it reaches up to the surface and it gets reflected. And let's say that this reflected surface is my free surface. When it reflects back from a free surface, it has been experimentally noticed that there is no change in their phase. There is no change in the phase. How do we come to know theoretically that there is no change in the phase? Now tell me, after this, take an example over here. After this, where should the wave be propagating? Or the particle of the medium will be vibrating where? In the upward direction or it's in the downward direction? After this. Downward, okay. So it will actually go in the downward direction like this. So the particles will be vibrating downwards. It will reach up to one point and from there it will start moving in the upward direction. The particles will move in the upward direction up to here. Now, same thing happens here when there is a free surface, no change in phase. So that means after this, when it reflects back, the particles should go in the downward direction. That means if I show this, the particles should go in the downward direction. So the wave what we get here after reflecting will be something like this. So the particles are going in the downward direction. So there is no change in the phase after reflection. And from here it will go in the upward direction. And then it goes in the downward direction. So this is my reflected wave. And this is my incident wave. So it's like this. And it gets reflected from the surface. Reflected wave is this. Did you get it? What is the meaning of reflecting a wave from a free surface? Free surface, there is no change in phase. So actually no change in phase, it's like this. You notice just now here, the particle should be vibrating in the downward direction, so it's downward. So when it reflects back, my particle is vibrating in the downward direction and it goes like this. So such kind of a wave has no change in phase difference between the particles over it. So this represents the reflection of the wave from free surface, and wherever they superimpose or they get superposition, there we get the stationary wave. So when you see this, you will notice that there are three loops, but all these loops are vibrating at their own position. That's why we get such a wave as the standing or stationary wave. Is that clear? I'll show you one more example, but that example will be not respect to the free surface. Now we'll discuss with respect to rigid surface. So write it down what you have understood so far. Quick. All right. So let's just go ahead and we discuss what happens when such a ray is reflected from a rigid surface. You will come to know only after seeing the proper diagram. So let's say that this is an open surface. There is no reflection happening. So this is my way traveling like this. Let's say that there is a rigid surface. And what should happen at the rigid surface? You come to know now. Now, let's say that my wave is traveling and it reaches up to such a surface which is my rigid surface. So let's say I draw a rigid surface something like this. So this is my incident ray. My incident wave reaches up to one point and this point is my rigid surface volume. What will happen now? There will be a reflection taking place here also and the reflection will be taking place with respect to the rigid surface. Now what happens is that if we look into this diagram again, this particular diagram, what should happen over here is the wave which should go downward. When the wave goes downward, the particles are vibrating in the downward direction here. So they are in the same phase. Imagine, in this case what happens is that the reflected wave, what we get is out of phase. And experimentally it has been found that when it is out of phase, it's out of phase by 180 degrees, 5 radians. So when I want such a reflected wave to be out of phase, after this point, my particles should not vibrate in the downward direction. The particles should vibrate in the upward direction. So how it starts vibrating in the upward direction? Isn't it that after reflecting, my wave will not go something like this? Because if it goes something like this, the particles are vibrating in the downward direction. So my reflected wave should go something like this. So if this is my incident, my reflected wave, if I draw here from this end, which is O, if this is my incident wave, my reflected wave will be something like this, because after this it should go downward, particles should vibrate in the downward direction, but no, the particles will be vibrating here also in the upward direction, so it goes something like this, and then it goes something like this, then it goes like this and comes up here. So this will be my reflected wave. This particular wave will be my reflected wave and they both will be out of phase. And they are out of phase by 5 radians. This is my reflecting surface, which is a rigid surface. This is my rigid surface. Draw this diagram. Alright. So basically we say that this is nothing else but it's a reflected wave. You write this also a reflected wave. Alright. So far is this clear that how does the reflection takes place? It can be from free surface, it can be from rigid surface. I hope you are getting it because it's very important and we'll be using this concept in finding that what can be the outcome when the waves reflect from the free surface and when the wave reflects from the rigid surface. Very important to understand this. If this is not difficult, but yes, may cause some issues if you are confused in this. So let's go ahead. So what happens when such two waves that is incident and the reflected waves, they superposition each other. We get standing waves. But what is the condition to get the standing waves is that these two waves should travel in the opposite direction of each other. And we noticed just now, my incident ray is going in this way. You know my reflected waves, how it goes. This is my reflected. So my incident ray is in one direction, my reflected wave is in the other direction. So one more condition to get the standing waves is that my incident wave and my reflected wave, they both should be in the opposite direction. Wherever they get superposition, we get the resultant displacement. And we'll see and we'll find the equation of resultant displacement also over here. Now, very important to understand, whenever such two waves, incident and reflected waves, interfere. Let's say that I have two rigid surfaces and I get such a loop. Okay. Now in this particular loop, what happens is that the certain particles of the medium here, will see, they will vibrate at their own position. That is this position. We call this as a rest position, mean position. And certain particles goes at the maximum displacement. That's the amplitude. So here also it's maximum displacement, amplitude over here. We call them with certain name. Wherever these two waves superpositions and there are resultant displacement over here is actually zero, we call such points as nodes. And wherever there is a maximum displacement, we call such points as antinodes. Draw this diagram to make you understand what is node, what are nodes and antinodes. Okay, so to understand that, we need to know that there is the equation for the displacement of the progressive wave. Can anyone tell me what is the equation we use for a progressive wave? Or the displacement of the particle? What? One. Class, you have done this chapter earlier. So tell me. No? Okay. Y equals to A sine 2 pi by lambda dt minus x. Such a particular equation of a wave, it indicates that it's a progressive wave and it is progressing in the direction of positive x-axis. So let's say that I have a particular wave whose displacement equation is given in this way, where all the variables, all the notations, they have a usual meaning. But we indicate such an equation when a wave is traveling in the positive direction of x-axis. Write it down this. So this is my incident wave in the direction of the positive x-axis. Then what can be my reflected wave be? What can be my reflected wave? It's the same. It's y equals to a sine pi by lambda plus x. This minus x will change into plus x. That will be called as a reflected wave. Okay. And we are discussing this reflected wave with respect to a free surface. So basically you should write my incident wave and my reflected wave in a free surface, because there is no change in their phase. It's only the change in the direction. We'll come to that type of equation also. All right. When it is done, let me tell you, if the reflection over here is taking place not from a free surface but from a rigid surface, how this equation will transform into, let's say I have y1 over here as the displacement of my incident wave, y2 is the displacement of my reflected wave from a free surface. Okay, so you better understand this in a free surface. Let's say that this reflected wave is not from a free surface, but it is reflecting from a rigid surface. How there will be a change in phase? Can anyone tell me now? The phase change will be by how much? Yes.
180 degree.
180 degrees, correct, and that's what I explained also. So there will be a phase change in my reflected wave by 180 degrees. That means if I take this as whole angle as theta and I write this as plus phi, I write this as plus phi, so it will be sine theta plus phi. When you simplify all that, you get this equation as y2, which is my reflected surface, in a rigid surface. I get this as y2 equals to minus of a sine 2 pi upon lambda dt plus x. Everything remains the same except I get this minus sign because it's a math and you should know that this plus pi will give me the answer as minus this. Write it down this equation. Alright. Let's come to very important point now. So far, what we did bonded region. Under bonded region, we did free surface, we did rigid surface, we did the reflection through the free surface, we did the reflection of the wave through the rigid surface, we did the equations to be written when it's reflected from a free surface, when it is reflecting from a rigid surface. Now, very important over here is when such two waves, one is the incident wave, the other one is the reflected wave, they both combine each other. They superposition each other. There has to be some resultant displacement, and let's say that I take that resultant displacement. I just for time being take y1 as the ray, sorry, y1 as a wave in one of the medium that is in the direction of positive axis, and let's say that it is reflected back from a rigid surface. So this is the equation for this is the equation for the reflected wave from a rigid surface. I want the resultant displacement, which I write as y equals to y1 plus y2. So my resultant displacement between this incident and the reflected wave from a rigid surface is y equals to y1 plus y2. Therefore, I substitute this y1 over here and y2 over here. I get, I'm not showing you and I'm not writing the whole equations over here. I'll just show you that my A in both this equation will be a common, correct? Or if I take minus and outside plus, that's not the issue. Here, only the thing is that to understand sine C plus sine D formula is what? And sine C minus sine D formula is what? Once if you know this, any kind of equation you can simplify it easily. So in this case, if I take a minus A also common over here, what will happen? How my equations will transform? If I take this as minus A common out from here, that is this. I can write this as sine of 2 pi on lambda dt plus x. Minus is outside. So this plus should transform into minus. So it's minus sine of 2 pi upon lambda dt minus x. I get this as the equation. Now, it's only the math over here. I take this whole angle as C, sine C, minus this whole angle as D. Come on, sine C minus sine D. Anyone knows what's the formula for sin C minus sin D over here? If you know, go ahead. Come on, quick. You can do it. Tell me the answer of y. That's minus a. Apply formula sin C minus sin D and tell me the final answer. Wait. Okay. We don't have much time, but definitely you would have got the answer. I'll give you what can be the answer over here. This is minus a, so you get minus 2a. There will be one term with cos with some angle, and there is another term with sine with some angle. This much you should get the clear-cut idea, because sin c minus sin d is 2 cos c plus d by 2 sin c minus d by 2. So if you apply that formula, you get this equation as 2 pi dt in the numerator, and in the second term, which is sine, there is no time related, it's 2 pi x because it's displacement again. So we have 2 pi dt upon lambda, and here also 2 pi x upon lambda. This is the equation you should get when you simplify with sin c minus sin d, and you should get this as the answer. Thank you. Take care.